This lesson is on topic 1.3, which talks about vectors and scalars. In terms of understandings, we need to be able to differentiate between vectors and scalars. Those are the two types of numbers that we're going to be working with. A lot of our work deals with vectors, and we need to be able to separate vectors between angle and magnitude and the x and y components. The IB limits us to two-dimensional vectors only, but in IB Math, you also look at three-dimensional vectors. In terms of how we will be applying vectors, a lot of our formulas deal with vectors, so we will need to be able to work with those vectors in an algebraic format, but we also need to deal with them graphically. First off, what are vectors? Okay, vectors are numbers that have both magnitude and direction. It's important that the direction represents where we are traveling or which direction the force points. The direction is important. Never forget that when you're talking with vectors, there's a directional component, and that direction can change while the magnitude doesn't. We'll see that especially when we talk about circular motion. Okay, the magnitude in general should always be positive. Okay, a negative vector simply indicates a positive vector in the opposite direction. Okay, besides the magnitude angle format, we'll also be looking at the component format. How much does this vector point along the x-axis, and what percentage or what portion of the vector points along the y-axis? That's considered the component format. Scalars, on the other hand, have just a magnitude. There's no direction associated with them. Okay, it doesn't matter where they point because they have no direction. Okay, a direction for mass, for instance, is meaningless. Okay, scalars, however, can be both positive or negative. Temperature is another example of a scalar. There is no direction associated with temperature, but you can easily have a negative temperature, especially in the Celsius or Fahrenheit scale. So, examples of vectors that we will encounter are displacement, how much and in what direction have you moved, velocity, what direction and how fast are you moving in that direction, acceleration, how fast is your velocity changing and in what direction is your velocity changing, force, momentum, the fields, the various fields that we will be working with, which include the gravitational field, the electric field, and the magnetic field. Those are all examples of vectors that we're going to be working with. Examples of scalars. Some of these scalars are very similar in definition to the vectors, but they're the directionless portion. Okay, distance and displacement, similar. Speed and velocity, similar. Speed is simply the magnitude portion of velocity, and other examples are mass and time, charge. Current is a little bit weird, okay? Current does have a direction in the sense that which way around a circuit is my current going, but we still consider it to be a scalar because it's not a true vector. Okay, energy is another scalar that we have, as well as voltage. These are all values which direction doesn't really make any sense. So let's look at the two formats, okay? The magnitude of a vector represents the scaled length of the vector. As long as I don't change my scale, a greater vector, greater magnitude indicates a greater length. Okay, the angle, by convention, it starts at 0 degrees, which on two-dimensional plane corresponds to east as shown below. Okay, positive angles will go counterclockwise. So starting from 0 degrees, 90 degrees would be straight north, 180 becomes west, and 270 becomes south. Negative angles, which are perfectly acceptable, would go the other direction. Okay, this is simply convention. If you change convention, okay, you must write it down somewhere on the paper that says positive direction is going to go clockwise, or I'm going to start 0 degrees is north. Okay, negative angles, however, so negative angles would go clockwise, positive angles go counterclockwise. In component format, this represents how far the vector moves along the x, y, and z axis. Fortunately, we're limited to just two axes, so we'll be looking only at the x and y axis. In this class, in IB Math, like I mentioned, you will have a third axis. Okay, I will be using the letters I hat, J hat, and K hat. These are common vector component nomenclature to represent the displacement along the x-axis, the y-axis, and the z-axis. So I'll primarily just be using I hat and J hat. Okay, and they basically just represent a unit vector in one unit along the x or the y-axis. So for example, I have a vector here. A vector is equal to 4 units along the I-axis or the x-axis in other words, and 4 units along the j, both in the positive direction. So this is the vector represented by the vector shown in the graph. Okay, all 3 of those vectors are the same. Okay, so it's important to realize that there is no real origin or start to a vector. That start point is movable. Okay, in magnitude angle format, this is the same vector. It's 4, has a magnitude of 4 square root of 2 at an angle of 45 degrees. So you could easily, if you had a ruler, graph this as the same vector as 4I hat plus 4J hat. So in terms of these two notations, we'll need to be able to convert from back and forth from magnitude angle to component, and then back from component to magnitude angle. Okay. Since the vector is frequently at an angle, it will have both an x component and a y component. Those components can be negative. Okay, components are not magnitudes. Okay, so they can be negative. So in this case, I have a vector. A vector has a component a sub x in the I direction or x direction plus a sub y in the j direction. Either ax or ay can be positive, negative, or even 0. If one of the components is 0, that implies that it's just a one-dimensional vector. If both of the components are 0, this is the 0 vector. Okay, a 0 vector has all components equal to 0. Converting between the two formats, going from a component format to the magnitude angle format, requires you, the magnitude is simply, remember, the length or the distance of the vector. So this is the distance formula, x squared plus y squared square root. I call that the Pythagorean sum, but it's really the distance formula. The angle is a little bit trickier, okay? It requires you to put a little bit of intelligence, especially if you're using your calculator. The problem with your calculator is it doesn't know what quadrant you're working in. Okay, so in terms of angle, yes, you're still going to be doing the inverse tangent of the y component over the x component. Okay, this is simply the inverse of opposite, which would be y, over adjacent, which would be x. Okay, so those are the components. X and y are the components along the x and y axis. Okay, you need to make the appropriate adjustment for the appropriate quadrant. Okay, so in the first quadrant, there's no adjustment necessary. In the second quadrant, you need to be careful because it's frequently going to be 180 minus that angle. In the third quadrant, it's going to be 180 plus the angle. And in the fourth quadrant, you could probably simply express it in the fourth quadrant as that angle in the negative direction. Okay, to convert from the magnitude angle format to component format requires you to use the trigonometric formulas. Okay, the x component is going to be the magnitude times the cosine of that angle. The y component is going to equal the magnitude times the sine of the angle. Okay, we need to be very fluent with this conversion between formats and not have to spend time thinking about how do I go from one to the other. In terms of algebra, the primary function that we're going to be doing is vector addition. Okay, and when we do vector addition, there's two ways we do it. Okay, we only add the components. Okay, we don't add in the magnitude angle format. Okay, except graphically. when we're doing vector addition of the components, all we do is we stack the two vectors vertically, and the various components just add up. Okay, so in this case, we take the AX's and the BX's and just add them together, and we end up with AX plus BX, I hat, and AY plus BY, J hat. Okay, so if some of those numbers can be negative, that's fine, in which case we're adding negative numbers. That's okay. Graphically, we need to be very careful here in that the vectors can be added using a tip-to-tail method. That's the primary method that we work with. Okay, the various books have slightly different methods, but I like to teach the tip-to-tail method. Okay, when I use the tip-to-tail method, the warning I want to make to you is that the tip of the first vector must be followed by the tail of the second vector. In this case, as shown, I have an A vector and a B vector. Notice that the tails of the two vectors are touching. This is not how we add our vectors. Okay, that second vector must be moved so that its tail starts where the tip of the first vector finishes. Okay, then the resultant goes from where the first vector started to where the second vector ended. And that's going to be called the resultant. So what's shown here, after we make the necessary modifications, is that C vector is equal to A vector plus B vector. And again, C is called the resultant. If we're subtracting, remember, all we're doing when we subtract is we're taking the second vector and flipping it. Okay, that's similar to doing adding the negative of the second vector. We'll also be doing vector multiplication. Okay, there are three different types of multiplication. Really, only the first one is required to be known, but the other two are useful, and I will go over them briefly. Okay, the first one is multiplication by a scalar. This is what we do when we just multiply it by another number. It changes the length or magnitude of my vector. That's all it does. So the magnitude would get multiplied up. If it's in magnitude angle format, it doesn't change the direction. Okay. If it's in component format, all I do is take those components and multiply it by whatever that scalar number happens to be. Okay. It just changes the magnitude by that factor. The dot product is one method of multiplying two vectors together. Okay. We see this in various formulas. Last year we kind of just glossed over it without saying why it was that way. In IB Math, you do talk about the dot product and use the dot product. Okay, in this case, all you're really doing with a dot product is you're trying to figure out how much of that first vector is parallel to or in the same direction as the second vector. Okay, so what you're really doing is just taking the magnitude of the first times the magnitude of the second times the cosine of the angle between the two vectors. Okay, we've seen this last year in the formula that said work is equal to force times distance times the cosine of the angle theta between them. Okay, well, what we really did was it's a dot product of the force and the displacement vector. The cross product you don't even discuss in IB Math. Okay, however, we run across it in different formulas, and in particular when we get into the Lorentz force or the magnetic force on a charge. The result of a cross product is another vector. The result of the dot product that we just talked about is a scalar. Okay, but the result of a cross product is another vector. And the resultant vector is going to be perpendicular to both of the original vectors, and we'll talk about that direction when we get into the right-hand rule much later in this year. But most of the time when we work with the cross product, we aren't that focused on the direction. We are primarily concerned with the magnitude only. In that case, all we're doing when we take the magnitude is we're taking the first vector, the magnitude of the first vector, times the magnitude of the second vector, times the sine of the angle between them. Okay, this finds the perpendicular amount, okay? How much of the first vector is perpendicular or in the same direction, or in the perpendicular direction to the second vector, okay? So that's what we're really doing, okay? We're just looking for how much of that first vector is perpendicular, or another term that we'll use and that you'll encounter there is normal, okay? Normal and perpendicular are going to be similar terms. Thank you.